For this question, it says how many, well, it can ask sigma or pi bonds. And I've changed this question to say how many pi bonds are there in carbonate ion. So our definition of, well, let's start with a sigma bond. So let me define a couple things down here. Sigma. A sigma bond is a bond in which the electron density lies along the axis between the two nuclei. Lies along the axis of the two nuclei. While a pi bond is a bond in which the electron density lies, so dot, 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 electron density lies above and below the two nuclei. Sorry about that. Let me get this on screen there. Above and below the two nuclei. And we'll talk about this quite a bit. I'm actually going to start with question 2 first here. And question 2 says, how many pi bonds are there in C2H2? If we draw the best Lewis structure, we will find that there is a triple bond between the two carbons. And one way to remember it is that the first bond between any two atoms is a sigma bond. And another way of doing it is that a single bond is a sigma bond. Other bonds are pi bonds. So if you have a single bond that is sigma, if you have a double bond, the first one is sigma and the second one is pi. And if you have a triple bond, it's sigma, pi, pi. Now, if we were to do an analysis of the sigma and pi bonds, well, there are actually 2 pi bonds. And I don't know, any triple bond is 1 sigma and 2 pi bonds. So we do have 2 pi bonds in this molecule. In this entire molecule, we also have 1, 2, 3 sigma bonds. So 3 sigma bonds. And 2 pi bonds. Now, and one other thing I'll say is the way that I write the lowercase Greek letter sigma is a circle with a hat on it. So that is a sigma symbol for me. And pi, well, maybe we're used to pi. I think most people draw their pi at least something similar to this. Not so sure about sigma, but that's how I draw it. Now, what I'd also like to do is I'd also like to draw this molecule in two different ways. I'd like to draw it, and I'll flip it over and redraw its Lewis structure. So this is C2H2, best Lewis structure. And what I'm now going to do is I'm now going to draw what's called an orbital overlap diagram. And in an orbital overlap diagram, you literally show the orbitals overlapping. And here's our process for this. Boy, doing all this chemistry, making me sweat. All right. So here's what our process is going to be. Now I'm going to look at this carbon. This carbon has 2 electron groups. And if it has 2 electron groups, that means that its hybridization is sp hybridization. And if I go to the other carbon has the same thing. The other carbon has 2 electron groups as well. 1, 2. And a triple bond is still 1 electron group. Yep. What that means is when I draw my orbital overlap diagram, that I'm going to draw my carbon and my other carbon, and what sp hybridized orbitals look like is 1. So this right here is an sp hybridized orbital from this carbon right here. And actually, I wonder if I can do this in different colors. So there we go. And this is an sp hybridized orbital, zoom in, for the other carbon atom. And when they overlap, they will share 2 electrons. And because this is between the 2 nuclei, this is a sigma bond. Now, like I said, sp hybridization means that there are 2 hybridized orbitals. What's in red right here is only one of them. Now I'm going to draw the other one. And this is an sp hybridized orbital for that carbon. And here's the other one on the other side. So each carbon has 2 orbitals, and each orbital is an sp2 hybridized one so far. Now, let me draw the H. H, if you remember, has just an electron configuration of 1s1. So when it bonds, it's going to bond with its 1s orbital. And hydrogen brings 1 electron, and carbon brings 1 electron as well. The same thing on the other side. I'm drawing the 1s orbital, and hydrogen brings 1 electron, and carbon brings 1 electron. And so now I've drawn all the sigma orbitals. I still have some pi orbitals to draw, and all the sigma orbitals lie along the axis of the nuclei. I'm not done, but any questions so far about this? Okay. Well, now, So let's think about this carbon atom for a second. So a carbon atom has, and it has a 2s orbital and 3 2p orbitals. One of them is hybridized, so and leave some space around this because the pi bonds go above and below, remember. But I'll back up a little bit and say, so, and I'll say each carbon has 3 2p orbitals. Only one is hybridized. Only one is hybridized, which means 2 of the 2p orbitals on each carbon are unhybridized or normal. And by normal, what I mean is, okay, so here's an axis. This is 2py because it's along the y-axis. And 2pz would be coming out of the page at us and going back into the page. So this we might call 2pz. And I'll point out to you, so this is just a regular orbital. So what I'm going to do now is, and they're a little far apart, but I'm now going to draw this is 2py. And on the other atom, this is 2py. And unfortunately, I've drawn them a little far apart, but what I want to say next is that the pi bond forms due to the overlap of the 2p orbitals, or 2py orbitals. And to go one step further, somewhere within those 2p orbitals are also 2 shared electrons. And it doesn't matter where you draw them. You can draw them both up top or both down here. What we're saying is that the 2 electrons go sort of like this. They can be anywhere in this orbital. Let's remember what orbitals are. Orbitals are volumes of space in which you find the electron 90% of the time. And what we're saying is that in one of these double bonds, there is a pi bond formed by the overlap of the 2py orbitals in which there are 2 shared electrons. Now, that's one of the pi orbitals. The other pi orbital is going to be 90 degrees to it and come out of the page. And let me see here. So, and one of the things I've asked you to do for the homework is to actually model and make a 3D model of a pi bond. And what you can do is you can actually take a piece of paper and build it out of the page. And this is going to represent the 2pz orbital. And what you might do is from this carbon, you draw a little shape like this. And call it 2pz. And it's even color coded according to mine. You don't have to color code it. And then on the other side, you have a 2pz from the other atom. And so it sort of looks like this. So let's see if I can get a better angle at that. And finally, you draw the overlap and put in an electron. And so what I would then ask you to do is to tape it down. See, this is the red part. So that you can see that this second pi bond is perpendicular, also called orthogonal, since it's in an orthogonal plane. And so I'm showing that this molecule has a three-dimensional aspect to it. And in a perfect world, you would also do the other half down on the other side of the paper, but I will take at least something being three-dimensional. And when we get to that problem, I will say we will do, actually I don't know if we're going to do this problem because I'm doing it right now, but you need to do something that is literally three-dimensional. And this is three-dimensional because it's got that shape coming up. Any questions about this? This is going to be my, oh, I guess I should say this is another pi bond. That's another pi bond. So now we have one pi bond. These two parts are one of the pi bonds, and the other pi bond, I'm showing one of them, and then there's another half to this pi bond that's actually underneath of the piece of paper. That is an orbital overlap diagram. I guess the one thing I forgot to mention about this is I do ask you to label this as a sigma bond, this is a sigma bond, and right in the middle here is also a sigma bond, and this is a pi bond, and this is a pi bond as well. But what I really like about orbital overlap diagrams is that you really see, like, a bond is made from the overlap of one orbital from each atom. And that's really clear in this. I'll stop recording. Questions?